Thank you for the introduction. So, how to write correct and organizers for this printed topic is. So, in this talk, we discussed about some functional Borel products, and especially interested in the relation between the functional Borel product and the heat flow. And this talk is based on the Shohei Nakamura. I don't know. He's in this place, but I can't find him. But I'm just asking. Yeah, he's the Shohei Nakamura. And this talk is topics in this talk is already that for the archive apart from free.
Yes, no. The second button is the second one, the middle one is long.
Yes. And okay, there are today's topic is already done. That type and the second one. Basically, some observation is already appeared in the second papers. And that is the overview of this today's talk. And so the based on our interesting ingredient is that the volume product, which is the product of the volume of the convex body and its polar body. And about that quantities, the basic problem is that the basic problem is known as the Brasque-Sunshine inequalities or the Mara conjecture. They say that in that problem we consider the prime of the volume product or the infimum of the volume product. Now in this talk, basically we are interested in only the Brasque-Sunshine inequality and we don't care about the Mara conjecture. And moreover, in this talk we consider functional version of them. The functional, so to see formalities, we should consider functional quantities of the volume product. But then already formulated by these balls and Einstein and Pratt Newman. And they gave that as a volume product, the product of the integration of f and v and time the integration of f circle. And here the f circle is given by this guy. Actually, this guy is related to the Legendre transforms. But I will also mention about it later. And we investigate about this quantity, but we do not deal with guys, and we consider some regularized function volume product in this way. This means that we consider these guys, those guys. Here, the PS and QA is given by this one, and gamma is a standard Gaussian, and PS is always dynamic semigroups. Okay. So then we can observe that if s goes to 0, then this guy converges to the function volume product. But this observation is already known by the work by the Bobkov-Gentil-Ledoux, in which they show that the smoothing property of the heat semigroups imply the hypercontractivity of the Hamilton-Jacobi semigroups. And especially in this case, Hamilton-Jacobi semigroups is actually related to this F circle, or related to the Legendre transform. Okay. So let me explain more precisely our detail. So in this talk, so let K be a convex body, and especially suppose that the origin is included in the interior. And then the polar body of K circle is defined by that one. Okay. So for example, if you consider the unit ball of the LP space, then the polar body is the unit ball of its dual space, especially in this case, the T5. And then the volume product is defined by the product of the volume of K and its polar body. And it is very known that about this guy, the V is linear invariant. Then the Brasque-Sunshine inequality states that for any symmetric convex body, the volume product is maximized by the standard unit ball. And more equality holds if only if there is K is a symmetric ellipsoid. This ellipsoid comes from the fact that the volume product is linear invariant. Okay, so that in this talk we want to consider about functional version. So next let me explain the function volume product. Okay, so the function volume product is defined by product of the integration of f and the integration of f circle, and especially if f is given by the e minus psi, then f circle is actually given by e minus psi. Here the psi star is the geometric transform. Then actually this function volume product is related to the volume product for set. Because for example, if you take a gauge function of K and consider the functions, these guys, then you can consider the volume product for these guys, then you can calculate completely and actually you obtain the volume product for K. So therefore, we can consider this function volume product as a generalization over this function volume product for set. Okay, so about this, guys, also the function Brasket-Hunter equality is known. So the function Brasket-Hunter equality says that for any even functions, or then if you suppose the percentage is 0, then the function volume product is maximized by the Gaussian. Okay. And moreover, equality holds if and only if f is a Gaussian measure whose covariance is any non-degenerate matrix. Okay, so just I mentioned that this function Brasket-Hunter equality means that the function volume product is maximized by Gaussian and geometrically maximized by the pole. And one of the proof to obtain this inequality is Steiner symmetrization, I think. And this means that if given a convex body K, then by using a Steiner symmetrization, you can construct some monotone increasing, you can construct some sequence of convex body by using a Steiner symmetrization, which suggests that the volume product is monotone increasing, and moreover, this convex body converges to ball. So therefore, the result you can obtain the Brasket-Hunter inequality for set. Especially, I want to emphasize that this guy is monotone increasing around the Steiner symmetrization. And similarly, we can consider the functional version of the Steiner symmetrizations. And already is mentioned by the Arstein, Arden, Pratt, Millman's work, but in that case, we cannot obtain the Gaussian measure directly, and just only we obtain the radial functions. This means that the n-dimensional Brasket-Hunter inequality, the problem of the n-dimensional Brasket-Hunter inequality is just only reduced to the one-dimensional problem. But we cannot obtain the Gaussian measure by using this method, so we should then show the one-dimensional Brasket-Hunter inequality directly. Okay. As another observations, in another point of view, for example, we may consider the some similar monotonicity also. No, for example, by using the heat flow. For example, if we consider the chance entropy, we don't give a definition of it here precisely, but for example, it is well known that chance entropy, for example, is monotone around heat flow. And as a result, for example, you can obtain that the Shannon's entropy equality. It means that the entropy is maximized by the Gaussian under some constraint of the variance, for example. And actually, this phenomenon is similar to the functional Brasket-Hunter inequality. Okay, and so in this talk, we also consider the monotonicity of the functional volume product around the heat flow. And to explain our result more precisely, we introduce what is a heat flow. In this talk, we consider Fokker-Planck solutions. This means that if given a non-negative function is 0, ft is a solution of that equation. Yeah. Okay. And it is about this ft, it is meant that there one integration is preserved. This means that the mass conservations. Okay. And moreover, if t goes to infinity, this function converges to Gaussian. Especially we can capture the Gaussian measure directly. Okay. Then if we consider this solution, we can show that the volume product is not increasing if the initial data is even. So more precisely, this quantity is non-decreasing. And actually, if you believe this monotonicity, you can obtain the Brasque-Sancho inequality easily. Because, you know, the F0 is better than the F infinity in some sense, because this guy is non-decreasing. So, and F infinity in some sense means the Gaussian measure. So therefore, I can say that become this being the function models plus the function. And to show this monotonicity, it's a simple idea is to calculate the derivative of these guys. And then you net, if you consider derivative of this, then you net this quantities. And I think this guy is actually related to the derivative of the Legendre transform, and such a guy is already mentioned by the Garina in this talk this morning. But in this talk, we don't calculate directly these guys, and instead of it, we consider some regularized version of F circle. Yeah. Okay, so how to regularize these guys? Okay, so to consider regularization, we use the Ornstein-Lembeck semigroups. Ornstein-Lembeck semigroups is that for any non-negative function h, the PSH is the Ornstein-Lembeck semigroups, and PSH is defined by these guys. Then actually this PSH solves that equation. Yeah. Then I should remember that this, if you consider the Fs, which is the product of PSH time the gamma, then this Fs is actually the Fokker-Planck solution with initial data h times gamma. So therefore, the Ornstein-Lembeck semigroups is almost the same with the Fokker-Planck solution. Then we consider this regularization in this work. So here PS and QS is given by this. And consider this LQ norm. Then you can directly calculate these guys and you can obtain some Laplace transform terms. Okay. To obtain these guys, that PS and QS complete representation are important. And especially if S goes to 0, then PS and QS also goes to 0. And just now QS is that, so therefore we can check that this term converts to F circle. So therefore we can obtain that function group other than that. Okay. Actually, if we consider this regularization, we can also show, we can obtain the monotonicity of this guy along the heat flow. More precisely, P and Q are the same, then this LQ norm is non-increasing. And or equivalently, if you use us before this deformulation, then you can obtain that some guys of the Laplace transform is non-decreasing. We can show this one. And here we should remark that we here now we ignore this first integration because the integration of ft is preserved. Especially that integration of ft is independent of t, so therefore we don't care about this first part, and we only take care about the later term.
In the previous proof, why did you use the function as even?
Yes, yeah, we use this to use the evenness to show this. Okay, and proof about proof we will mention about later, maybe very briefly. Yeah.
In this identity, you don't need evenness.
You don't need it.
You don't need it. But sorry. To prove monotonicity, you need the evenness.
Yeah, proof. Yeah.
But for identity, you don't need that.
Okay. And actually, if you believe this monotonicity, you can obtain the monotonicity of the functional product, because as I just mentioned before, this guys converge the function Borel product. Okay. And moreover, not only obtain this monotonicity from that regularized version, you can also obtain some improvement of smoothing property. Okay, so next let me explain what is smoothing property. So first let us suppose that guys converge to the function Borel product. Okay, so then something we already know that Brasky Phantom inequality. So if you apply the Brasky Phantom inequality in the right hand side, then the right hand side is bounded from above by 1. So therefore, intuitively, you may expect that that LQ norms, we may expect that this LQ norm is bounded from above some constant Cs, which converges to 1 if S to 0. And this formulation is equivalently that this exact LQ norm is bounded from below by 0 because QS is negative. Then someone noticed that this formulation is actually for the reverse hypercontractivity. So what is the reverse hypercontractivity? Reverse hypercontractivity measures how much the positivity is improved under the heat flow. For example, if you consider the characteristic functions F and consider this guy, here we ignore the PS. Then you can check that this guy becomes 0 because this characteristic function is vanished outside of the Q. However, if we know the reverse hypercontractivity, then the right hand side becomes positive. So therefore, this guy is also positive. So therefore, in some sense, so reverse hypercontractivity means that the regularized function around the heat flow should be positive on the whole space. And moreover, actually, this exponent P and Q measures how much the positivity improved quantitatively. About this reverse hypercontractivity, originally Borell showed the following fact. If S is positive and if PQ are the real numbers, so then, and if PQ satisfies the first conditions, then the reverse hypercontractivity holds. And moreover, if PQ does not satisfy these conditions, if PQ satisfies the reverse inequality, then the infimum of the ratio of this guy becomes 0. This means that the reverse hypercontractivity does not hold. So therefore, this relation is very important. So PQ and S. And so we call this relation Nelson's time. Nelson does not appear now, but Nelson's name comes from the forward hypercontractivity. And Nelson originally showed the forward version of the hypercontractivity, so I use this name. Okay. Okay, so now let me back our situation then. In our settings, we consider P and Q as this one. Then you need to check that this exponent does not satisfy the Nelson type. Actually, if you consider Qs minus 1, Qs minus over Qs minus 1, then this becomes E4s. And actually, this is bigger than the E2s. So therefore, our framework does not include it in the Borell's reverse hypercontractivity. So this means that we cannot obtain the reverse hypercontractivity for general functions. However, we should also remark that the Brasky-Sancho inequality needs some evenness of input functions. So therefore, our problem becomes that can we expect the reverse hypercontractivity for this exponent if we impose evenness of input function? About this problem, the answer is yes, and actually we can show the reverse hypercontractivity for this exponent. Actually, moreover, so it means that if P, Q is negative and P is in 0, 1, and if P satisfies these conditions, then the reverse hypercontractivity comes. And moreover, this relation is optimal to obtain the reverse hypercontractivity. Okay. And about this result, in our previous works, we also already about the same conclusion, but in that case, the range of P is same, but the range of Q is smaller than this theorem 5. So this theorem 5 is the extension of the previous work. And moreover, the technique to show this reverse hypercontractivity is different from the previous work, because in our previous work we used the Fokker-Planck and Harnack inequalities and some partitions, which is originally used Lek to show the function Brasky-Sancho inequality. Okay. But in this talk we use the monotonicity of the heat flow.
So does this follow if you apply improved Gaussian Poincare inequality for even functions via sort of the methods of obtaining hypercontractivity from Poincare?
I don't know. I can expect it. Yeah. Yeah. I don't have enough good answer about it. Yeah. And also mention that this reverse hypercontractivity. So our reverse hypercontractivity is in the more general framework. In more general frameworks, this reverse hypercontractivity is related to some special case of inverse branch coupling. But in our condition is out of their conditions. So in some sense, our conclusion does not include in the framework of the Barthol's inverse branch coupling. Okay, that is a small remark, and we mention about it, more precise about it. Okay. Okay, so if you believe, okay, so how to show this file? Proof is very easy. If you believe this monotonicity of the regularized function Borel product, then if and let H be these functions, then H0 is exactly the left-hand side of the reverse hypercontractivity. And on the other hand, H infinity is less than the H0, and H infinity means if T actually becomes the Gaussians. And so therefore we can obtain the right-hand side of the reverse hypercontractivity. That is all, just proof of this of satisfied. Okay. And also remark that this monotonicity scheme, I mean this guy, yeah, is already is originally considered by the Aoki, Benefit, Karaman, Shiraki, and under the Nelson time. So, and actually, so therefore, by their result, then we can also obtain the reverse hypercontractivity, but under the Nelson time. And our technique is motivated by this. Okay, and then we also mentioned that our reverse hypercontractivity is formulated to the Laplace transform. Because as I mentioned, this QS norm is also can be written by this term, which is actually a Laplace transform. And more precisely, Laplace transform is defined by this. Then, if you use this Laplace transform, then we can deformulate the reverse hypercontractivity to this one. This means that if a Laplace transform of LPM of Laplace transform is bounded from by this guy. And actually, this inequality is equivalent to the reverse hypercontractivity, just I mentioned. So, okay, so maybe time is not so less, but we will explain briefly our proof how to show this T monotonicity. And the idea is simple to consider the derivative of these guys. Then, it more precisely consider the logarithm of these guys. Then you can obtain, so actually you can consider like this one. And so therefore our goal is to show this inequality. And to show these inequalities, we use two tools. The first one, there is the variance plus complete inequality in this sense. This means that there are some low concave functions, and if the function given a function phi, then the variance with respect to f is bounded from above phi. So. And then you can calculate. I'm so sorry, I don't mention what because I don't have enough time. Okay. And the second ingredient too is that the Cramer-Ram inequality. Okay. So then, and applying these two guys, then you can obtain the desired inequality. Like this one. And so therefore we can show the desired monotonicity. And okay, so, and I forgot to mention that the evenness is important to use the variance plus complete inequality. Because if we use the variance plus complete inequalities, sorry. Here as phi as exercise, and if small f is even, then we can check that the capital F is also even. So then capital F is the Laplace transform for that type. And so the second term of the left-hand side vanish if we use the evenness. So therefore we can apply the Laplace complete and then obtain the desired conclusion. Sorry. Yeah, that is brief proof of the monotonicity. Okay, so thank you for your attention. Sorry.